Thanks to the organizers for inviting me here, and thanks to you all for coming. Okay, so I'm going to tell you about mean estimation when you have the source code or quantum Monte Carlo methods. So throughout this talk, feel free to ask questions and interrupt. Yeah, I'm happy to explain stuff as I go along. Don't save questions to the end or anything. So my name's Robin. I work at Google Quantum AI, but this work was mostly done when I was at Microsoft Quantum. And this work is joint with Ryan O'Donnell, who's a professor at Carnegie Mellon, and he was also partly employed at Microsoft while this work was done. Okay, cool. So this is an outline of my talk. I'm going to tell you what is Monte Carlo mean estimation, what's the problem, and what do we do. And a one-line summary is that you can think of it as a primitive computational task that generalizes Grover search and amplitude estimation if you know what those are. And why is it useful? Well, one answer is because it generalizes these other primitives that are useful, but also it's used all over the place. And I'll give you some examples from scientific computation and finance. These are two places where it's used. And finally, I'll tell you a little bit about how we solve the problem, and talk's roughly divided into 3 parts of equal length, covering these 3 bullet points. Okay, cool. So let's start with the main problem. What is Monte Carlo mean estimation? So this is an idealization of the problem. You have some black box, which is depicted by this box that's black in color, and it knows a random variable. And what I mean by that is it knows inside it some probability distribution that I'm going to label P sub x, and it outputs a number x. Think of x as just a real number throughout this talk. It outputs some real number x with probability P sub x. And this P sub x is a valid probability distribution. And so, as probability distributions tend to do, they're all non-negative numbers and they sum up to 1. And your goal is to compute the average value of this random variable, which is like the mean, mu, which in other words, very formally is the sum over x of pxx. Okay. So the setup is clear. You just have this black box. So you just want to imagine you're interacting with this magical black box. You press this orange button on the top, and it just spits out an x with this probability distribution px. So you don't know anything before you start. You don't know what x's are. X's are just real numbers, and you don't know what this probability distribution, et cetera. Cool, so that's the goal. How would you solve this problem? Maybe we can make this part interactive. Does anybody have a proposal for how you would solve this problem? How would you compute the average value?
Sample many times.
Sample many times. Okay, and what do you do after you sample many times? What do you do with the answers? Take the average. Okay, good. Excellent. So that is an excellent thing you can do. And then the next question you might ask is, how good is this thing, right?
Like you said, we are not knowing x.
Sorry?
We also don't know x, right?
No, when you press the button, you get a little x out.
Okay, because then if you don't know the x, the sampling becomes very difficult.
If you don't know x, so you mean when you press the button?
You don't know what x is.
No, you get, you certainly know what x is once you press the button. Yeah, otherwise, I don't even know what you're going to do, yeah. So you press this button, and all you get out is little x, right? That's the only thing the back box gives you. It gives you little x. It gives it to you with some probability. Of course, you don't get to know this probability. It's not telling you what px is. It just tells you what x is. And as several people in the audience guessed, the one very good thing to do is just take a bunch of samples and output the average. And once you have this algorithm in mind, the next thing you might ask is, well, how good is this algorithm? How close is this estimate going to be to the actual number that I want, which is mu? And maybe many of you already know, one inequality that's going to help us to bound this is Chebyshev's inequality, and I'll tell you what it is. Chebyshev's inequality says that if you take around order n samples and output the empirical mean, which is just, take this number of samples, just output the average of the numbers you see, the estimate, mu hat, which you will output, with high probability will satisfy this bound, which is this mu hat will be close to the correct answer that you wanted, and the error will be sigma divided by root n, where sigma is the standard deviation of this random variable, and root n is, of course, n is the number of samples you took. And you don't need to know what sigma is so sigma is unknown to you, but this is the bound Chebyshev's inequality gives you, and if this is all you know about the problem, then this is the best you can do. If you don't have any further assumptions on your probability distribution or random variable, then the best thing you can do is just apply Chebyshev's inequality and hope for this, and take so many samples, and you'll get this guarantee, and this is the best guarantee you can hope for. And when I say this is the best thing you can do, this is the best thing you can do, whether you're a classical algorithm or a quantum algorithm. It doesn't even really, the question is just about how many times you're pressing a button on a box. So there's not something special a quantum algorithm can do. It's just a classical box. So whether you're talking about classical quantum algorithms, this is just the best thing you can do. Okay, good. Is the setup clear? This is the classic Monte Carlo mean estimation problem that has been solved for over 100 years.
When talk about what's the error metric?
Just number of samples. So,
I mean the error metric.
just this. I want to get close. So If I say that, I want to be as close as possible in absolute value to the correct answer.
Can't you apply some shrinkage? Like you shrink the estimated value so that the large samples, like, that's less harm. We can talk about that later.
Yeah. So you can prove sample complexity lower bound saying that this is optimal in general. So anyway, yeah.
If you say that's a classical box, what do you mean by quantum algorithms?
Yeah, exactly. I'm just trying to say that it doesn't. Yeah, quantum algorithms can't do anything because I haven't given them an opportunity to do anything because the box is classical. So right now this problem is just fully solved. There's nothing like. I'm kind of just summarizing what's known for over 100 years. This is kind of background. Yeah. I will now make the problem amenable to a quantum algorithm to actually make some progress on this question, right? So that's the high level question now, actually, which is it's a good segue, which is what can we do to this problem? How can we modify it in such a way that a quantum algorithm can do something for us? And one very realistic scenario is the following, where this X is not genuinely a black box. It's actually samples being drawn by you on a computer. Like you have a computer program that's generating these samples for you. So you have some code, maybe it's like written in Python or something, and it's sampling some X with probability Px. This is a situation that's pretty typical in scientific computing. You're trying to compute some mean of some crazy Markov chain, whatever, or maybe in finance. I'll give you some very concrete examples later where you have source code for this object, right? Like you wrote the code, it's in your favorite programming language. So thinking of it as a black box is it's too much of an abstraction. Like you've thrown away too much information. Let's go like one abstraction layer down and say that you actually have the computer program that generated this X with probability P of X for you. And what do I mean by that is, one example is just think of a classical randomized algorithm, which just, it's an algorithm either in a programming language or it's a circuit, however you like to think about algorithms, and it outputs some real number X with probability Px. If this is too abstract, we can make it even a little more concrete by thinking of it as a deterministic algorithm, so no randomness anymore. And what the deterministic algorithm does is it accepts a seed. This is the seed for the randomness. So the seed is some r-bit string, I'm going to call it I, and it outputs some number x sub I, some real number. And what you want to do is compute the average of these numbers xi. And so how many possible xi's are there? That's the total number of possible values of I, which is 2 to the r. So you want to compute this, does this pointer work? Yes. You want to compute this quantity over here, basically. Just sum up all the xi's over all possible seed values and divide by the total number of seed values. So I'm defining d as the total number of seeds. This is the quantity that we want to compute. And you can think of this deterministic algorithm as just like kind of encoding this super duper long string x of length 2 to the r. And you just want to compute the average of these numbers. So that's another way of thinking of having the code. This is actually without loss of generality. If you have a randomized algorithm that outputs some number x with probability px, you can always convert it to this form. So for the rest of the talk, actually, I'll just consider this situation over here because it's just going to be conceptually cleaner to work with. But this is okay as well. And the third scenario, which is actually strictly more general than these two, is that your algorithm, the one that was generating x with probability px, was actually itself a quantum algorithm, which is also fine. All the results I'll talk about will also handle that case. But that looks like this. So for those of you who know intuitively what it would mean to have a quantum algorithm that is the analog of this randomized algorithm, you probably had this in mind. But what it is, it's some unitary when you apply on some canonical starting state, let's say the all zero state. It produces a state, which is a superposition over the x's. Here you had a probability distribution over x's. Here you have a superposition, of course. The amplitude is the square root of the probability because the amplitude square is the probability after measurement. So this needs to match up with this probability over here. And in general, you might have some garbage entangled with your x. You can't have any control over that because how would you come up with this quantum circuit if you were given a classical circuit? You would just quantize the classical circuit. So this might have ancilla, it might have garbage. So in general, you might have this garbage around and you can't always assume that you have a pure quantum state with just the first part of this, like without this garbage. And in the quantum access model, I'm going to assume that you have access to this unitary, you can apply its inverse, and you can apply its control form. If you're not comfortable with this quantum version, just forget about it. It's not totally relevant because for the rest of my talk, I'll just talk about having access to this, but our algorithm works even in the more general situation. So if you like, you can just think you have a classical algorithm. Maybe you wrote it in Python or something, and it outputs some numbers x with probability px, and we want to compute their mean. That's the problem statement. Okay, good. This is a good place to pause for questions. Yeah.
I was a little confused by the notation on 2. So I is an element of 0, 1, or is that just like a length r bit string?
It's a length r bit string, exactly.
Okay.
Or you can think of it as a number between 1 and 2 to the r, whatever you like.
And then to the right of that, you have in curly braces I xi equals x. I don't quite get what you mean by that.
Oh yeah, so I'm saying like so. What is the probability of a given symbol x? Like x. These are real numbers. Right? Let's say what's the probability of seeing the real number 1, for example. So the probability of seeing the real number 1, so little x equal to 1, is the number of xi that equal 1 divided by the total number of possible i's. So that's the probability. Yeah.
Okay.
In the second scenario, are we allowed to quantize this function?
Yes, good. Right. So if I don't allow you to quantize this, then yeah, again, there's nothing you can do. So in the quantum model, either we'll assume this model over here, or we'll assume that you have this guy, which for the rest of the talk, I'll assume we have this. But what's different in quantum algorithms is you can make superposition queries over here. And you can do them in the standard way, which is that when you're trying to compute a classical function on a quantum computer in superposition, you get to compute it in some reversible way. So maybe you send in ket I in an empty register, and then you get back ket I, and in the second empty register, the value of xi is written down, or in other words, it's XORed with whatever's written there, whatever. You make a reversible version of this. So that's what's going to allow us to be quantum. Otherwise, we're back in like the previous situation where everything was classical and you have no quantum means of interacting with the object. Okay, so from now on, I'm just going to think about this model. You have some, which, as I said, you can forget about all this motivation of random variables and so on. You just have a d-bit string, which has real numbers written in it. You have standard Oracle query access to it, which means you ask the Oracle, hey, what's x sub I? And the Oracle tells you, oh, x sub I is equal to this number. And you want to compute the average. That's the new problem statement. You can forget about this random Monte Carlo motivation, if you like. And so what is the question? How many queries do we need to make quantumly to achieve the same error guarantees as before? So again, we want to estimate the mean as good as possible. And our result is the following. We say that we show that we have a computationally efficient quantum algorithm. That means the total number of gates that we use is also efficient. That uses only order n calls to this black box, and it outputs an estimate that satisfies this guarantee. And if you remember from a couple slides ago, in fact, maybe you don't have to remember, I have it on the slide. This is what you get from doing it classically using Chebyshev's inequality. The error goes like the standard deviation divided by square root of the number of samples. And what we get in the quantum world is you get the standard deviation divided by just the number of samples. So it's a quadratic speed up in the number of samples you need, which is great and very reminiscent of classic quadratic speed up quantum algorithms like Grover's algorithm, amplitude amplification, et cetera. And it's not a coincidence. In fact, those are special cases of this algorithm. So that's why there's a quadratic speed up. What is nice about our algorithm, and I pointed this out earlier when I talked about Chebyshev, the kind of the classical algorithm, which is just take a bunch of samples, take their average. You didn't need to know what sigma was before you did the algorithm, right? You just get some numbers, you take their average. The quantum algorithm has this nice desirable property that you don't need to a priori know what sigma is. You don't need to know an upper bound of the standard deviation. And finally, this is optimal for quantum algorithms because, as I said, like Grover's algorithm is a special case, and we know Grover's algorithm is optimal. So therefore, you can improve this. Yeah, so both algorithms work without knowing sigma or an upper bound on x. Okay, yes, I didn't even need to assume that you knew the range of these real numbers x. Cool, yeah, so that's our main result. Did that make sense? Yeah, correct.
So, do you know the additional overhead coming from, confidence intervals if you were to require higher?
I mean, certainly you can just multiply by log 1 over delta. Like I say, you want to do this with probability 1 minus delta, you can. Yeah, we didn't work out whether you. The other possibility would be that somehow additive or something, but I don't know. Mostly we just cared about the case where delta is 0.01 or something, so you just want to, with high probability, get the correct answer. Okay, go ahead.
So, and I think it was alluded to previously that there are like a median of mean estimators in the classical case.
Mm-hmm.
There are median of mean version of this theorem.
There's a word. Oh, median of means. Right, that's related to Rolando's question. So you classically use this median of means estimator when you want to get very high accuracy, like very high confidence in your, so not high accuracy. So by accuracy, I mean like this thing, like how far you are. But confidence means with what probability did you output a number that actually satisfies the property. So when you want high confidence, then you would use this median of means. But I'm just working in the scenario where the confidence is a large fixed constant, let's say 99%. I always just want to be correct with 99% probability. Then classically or quantumly, you never need to do any median of means business. You can always put that on top of this and drive the confidence even lower. So for example, if you want confidence 1 minus delta, you can just take our algorithm's complexity, multiply it by log 1 over delta, and you'll get, and that'll look exactly like median of means. It'll be, or not median of means, it'll be median of this algorithm.
So you apply this a couple times and
Take the median, exactly, and that always reduces, but it's just a general fact about all algorithms. It's nothing special to our algorithm, or even the classical algorithm. Okay, go ahead, yeah.
So I think you said that if we restrict ourselves to O of n samples, then this inequality is the best we can get. Does it also work the other way, that if this inequality is what we're going for, we really need all-of-n samples?
I see. You're saying like if you want an additive approximation of the mean to some constant multiple of the standard deviation, then you always need 1 over the whatever the constant multiple is, number of samples. Yes, yeah, you can prove that. Yep, okay.
Yeah, you mentioned it doesn't matter if you know the upper bound on x, but what if the upper bound of x is exponentially large? Does that still...
Right.
Then you...
So yeah, that's a good question. So first, okay, so there's 2 answers to that. One is if we're just talking about how many samples you need, or like how many times you need to query the oracle, then maybe we just don't even worry about the complexity of representation and so on, because all we're asking is how many questions do you ask the oracle. So it doesn't matter how much time you take on the side. That's kind of a answer just to say that like the sample complexity cannot depend on how big this number x is. But if you worry about like how would you actually do this algorithm, like what would the gates involve, then of course it would depend on how big the number x is. But in that case, yeah, that's right. So then the gate complexity will depend on how big x is. However, you can put some upper bound on how big it is before it's not worthwhile doing this at all. And you should take the source code that you have and completely brute force over all possible inputs. You can give that. Like there's always one trivial upper bound, which is just completely evaluate the function everywhere. So you can just, evaluate x1, evaluate x2, evaluate x3, all the way to evaluate xd, write all of these down on a piece of paper, sum them up, divided by d. That's always a correct answer. So you can never run more time than that. So, and that time is 2 to the r. So that's always a valid upper bound. So if your x's are somehow bizarrely large, you should not do that. You should, trivialize to this algorithm.
Yeah, I think that bound is coming from the central limit theorem. That is that x has to be polynomially bound. Otherwise...
Oh, this? You're saying that this doesn't hold if x can be arbitrarily large?
Yeah, so this is for bounded. But anyway.
But what does that mean? Like, so the random variable is fixed in advance. N only exists after the random variable, right? So the random variable cannot depend on n. So there's no notion of the random variable being polynomially dependent on n. Like the variable n doesn't exist when the random variable was defined, right? The random variable was defined first, and then I come in with my algorithm, and I have an n in mind. So the order of quantifiers is opposite. So it doesn't make sense to say that x is polynomially large or x is...
If the x grows exponentially as the size of that thing, and then you can't really just get the square root of it.
But the variance is finite.
Which is...
There is a sigma.
There's a sigma over here. Is that,
so you don't need...
Is that helpful?
If it
Okay.
works.
Okay, we can talk about this.
Right.
Maybe that'll help. Okay.
Yes, you're right.
Yeah.
This might not make sense, but does the high probability of your algorithm compared to the Chebyshev scale the same with the size of x?
Well, I'm using big O notation in both cases here. So like, so you're asking like.
So with high probability, I assume there's some like you get it within delta.
Let's say like 99% or something. I'm just thinking with high probability as like literally, let's say it's 99%.
That depends on the number of samples.
That's right, and I'm using big O notation over here. So like, I haven't told you what the constant is up front, but if you're asking like for the same 99%, like do I have a different big O constant inside the big O? I actually don't know. I have no idea. Any other questions? No, we're good. Okay. Okay, so let me give you an example of how the classic like search problem, like Grover's algorithm, is a special case of mean estimation. So you can see one example of where mean estimation is useful, and like you might also get some intuition for why it appears all over the place. So you can think of the Grover's search problem as solving the following problem, right? I'm given a d-bit string, and I'm promised that either all of the numbers are 0. That's the first scenario. Or you're promised that all of the numbers are 0 except one of them is 1, and you want to distinguish between these two cases. So if you think of them as random variables, this is the random variable that's always 0. Its mean is 0 and standard deviation is 0. That's very easy to compute. All good. If you think of this second random variable, which is 0 everywhere except 1 at one point, there's d points. So its mean is 1 over d, and its standard deviation you can compute. It turns out to be 1 over root d. And now if you apply our result, which says that the number of samples you need is sigma over n. So we want to approximate the mean to additive error 1 over d. So that'll allow us to distinguish between these two cases. And what we need is this 1 over d, so sigma over n should be less than 1 over d. Sigma we've already computed, so you can work this out backwards, and you'll get what n is, and you get n is root d, which is great, because that's what Grover's algorithm gives you. Grover's algorithm says that if you have a list of size d, and like all the numbers are either 0 or one of them is 1, then you can figure this, distinguish these two cases, root d queries. So that's a special case of our algorithm.
Slightly weaker version, right? It just tells you whether they're, which one. It doesn't tell you.
Whether there's a, that's right, right.
Refine.
You're saying it doesn't give you the label.
Give you J.
That's right, right. So, yeah, there is a, yeah, that's correct. There's some way to fix that, but let's not go there. Okay. Good, so Grover's algorithm is a special case, and in fact, several algorithms in the literature, as I mentioned before, amplitude estimation is also a special case. And here's a list of algorithms that we think are special cases. Of this, the first one is Grover that I talked about, BHT98, this is amplitude estimation. And then several algorithms have actually worked on the exact same scenario that we're thinking about, mean estimation of the Monte Carlo mean estimation. But they were, compared to our algorithm, they had some downside. Some of the early algorithms needed an upper bound on the standard deviation. Some of them needed an upper bound on both the standard deviation and the mean. And then the error was also based on the bound, not on the true sigma. Or they had more log factors in the sample complexity. So we get like the correct setting of parameters, the optimal setting of parameters, which you cannot do better than this, where your error will be sigma over n, and the number of samples is also order n. There's no log to the 3 halves or whatever. So that's our main contribution. Yeah, this is a good place to pause, because this is the end of the first third of my talk, and now I'll tell you about some applications of mean estimation, why you might care. But if you have any questions about the result itself or like what we proved, I haven't told you at all how we proved it. I've just told you what we did. But if you have questions about that, I'm happy to take them now. No, good. Everyone's good. Okay, cool. Let's talk about some applications. In no particular order, one application is, maybe this is the application that makes the most money. So maybe it's in the order of how much money you can make from applications. So this is the finance application. If you've heard of these things, pricing financial derivatives, computing gradients of financial derivatives, all these things called Greeks. Anyway, there's a bunch of these things that people in, I guess, investment banks or whatever do, and this is important for them because they want to, I guess, trade or compute fair prices of financial contracts like options and so on. A very large class of them end up using Monte Carlo mean estimation at the end of the day. So they do some probabilistic simulation of how the market will behave over time, and they'll like have some probability distribution over what the price will be of some, let's say you care about some specific stock, and you compute some probability distribution over what the price would be, and then at the end you want to compute, and then you might have some function on top of that. It's not just that you want to compute the average price, but maybe you have some kind of complicated contract that if the price is bigger than something, then you win some money, and if it's lower than something, you don't win any money, whatever, and you want to compute the average of this quantity. You can always express it as a Monte Carlo mean estimation problem, and this is actually what's done in practice. And there's a bunch of papers trying to do this in the quantum world. Here are just some random papers that I found. These were all written before our paper, so they all use older methods of quantum Monte Carlo mean estimation. I think you could go into any of these papers and use our methods, and you should get a speed up. So that's one reason why you might care, if you care about this application.
Could you give us an idea about how to construct the oracle in this
finance application, for example? Right, so in this finance application, so you have some stock or whatever, and you have some internal model of how the market is. Like this might be proprietary information, or you're an investment bank, and you have some information about like how you think the market will evolve tomorrow. And maybe your model is some kind of thing like, at every time step, like the stock price, I don't know, goes up with some probability or goes down with some probability. And what they do is literally run a simulation like this. They'll just go for as many time steps required, and they'll just keep running their model. And at the end, you'll get a probability distribution. This is some code you've written in Python or something, which genuinely samples x with probability p of x, where x is now the, let's say, the stock price of this thing, and p of x is the probability that the stock actually has that price tomorrow. So that this code, like the thing that's generally the proprietary information of banks, is the thing that is the code that I've assumed. And on top of that, you will do this Monte Carlo mean estimation. At the end, you might have some function as well of the thing, like the value of the price is above something or below something for an option, or if you have a more complicated contract, it might even be a more complicated function.
So every Monte Carlo pass is stored in word realization of your quantum qubits.
So think of the classical algorithm that does the Monte Carlo sampling. So it doesn't actually store every single path separately, right? It just has some seed randomness, and given a fixed value of the seed, it'll generate one specific path. So it's the same thing. So the quantum algorithm is just taking that specific classical algorithm and just making it quantum. It's just replacing all the gates by quantum gates. Yeah, so it's the same. So if you're, the other way to think about it is if your classical circuit used G gates, then your quantum circuit will also use ordered G gates. Maybe it'll be 4G or 8G or whatever, depending on the overhead of conversion. So it's the same cost. If you think of a classical gate and quantum gate as the same cost, then it's the same cost in number of gates. Of course, quantum gates are slower and so on. Yeah.
So your algorithm basically provides a quadratic speed up, is that right?
Yes, that is right. Any other questions? Okay, so that's an application to finance. Okay, let's maybe come back to applications that are perhaps more familiar to people in this room, which is a thing that you often want to do in quantum mechanics. You want to estimate the observable of a quantum state. So in a quantum algorithm, maybe what's happened is you've done some complicated quantum algorithm, like earlier today we heard about these algorithms for simulating dynamics of a quantum system. So maybe you did one of these dynamics algorithms, you created some complicated quantum state, ket psi, and now you want to measure some observable of it, like its energy or something. This is also essentially a mean estimation task. And why is that? So this is my abstract formulation. You have some quantum circuit, you created some ket psi, and you have some observable O and observable summation matrix, and you want to compute this expectation value, right, which is psi O psi to some additive error epsilon. Let's say you're happy with this kind of error. So how would you do it? Like one way to do it is you measure psi in the eigenbasis of O. So in other words, what I mean is if O has some decomposition, which is like O acting on the eigenvector lambda I gives you little oi lambda I. When you do this measurement, you'll get this little oi observed value with some probability, which is related to the inner product squared of psi and eigenvector. So this is again a mean estimation task, right? You have now view this object as a black box. You do this thing, you get a real number oi, and you get it with some probability. And what do you want to do? You want to compute the average value, right? Like that's the expected value of an observable. So what do? You store the outcome and you repeat this algorithm a bunch of times and you compute the empirical average. This is just mean estimation. So if you compute the observable on a quantum state, that's literally the mean estimation problem. And you can do it like this. I'm calling it the basic algorithm because it's kind of an obvious thing to do. And if you do it like this, the best guarantee you can prove, again with Chebyshev, is that you'll need this number of samples, where now you have to define what standard deviation means, but it means this thing over here. Or you can use our algorithm, and that'll give you a quadratic speedup. As I said, we get quadratically fewer samples. You might be thinking that there's another thing you can do, which is to use amplitude estimation, which is a popular classic quantum algorithm from 20 years ago. You can, however, what amplitude estimation needs is an upper bound on the largest value of the observable. So it would go something like this. You'll get a dependence on how big this random variable can be. So if your observable, that means how big the largest eigenvalue of the observable can be. So if your observable is of this type where it has a few large eigenvalues, but it's very unlikely that you actually have any support on that, amplitude estimation will not be a great idea because you'll suffer that. Whereas the standard deviation doesn't suffer this. So if you have some very large number, but it's very unlikely that you're going to be there, the standard deviation or the variance doesn't care about these large outliers. So this is why this can be much better than this. And of course, the standard deviation is always upper bounded by the largest number, the norm of this matrix. So in other words, the standard deviation of a random variable is always upper bounded by the largest value that a random variable can take. So this is, in terms of big O notation, it's a strictly better bound, but it might not be.
Here you're assuming you know the eigenbasis for O.
That's right, yeah. So this is, yeah. I'm saying, yeah, if you have a situation where you're thinking of this is how you would measure the eigenvalue, where you will go to the basis and it's a diagonal and you just do a basis measurement.
But your algorithm is also assuming access.
Yeah, exactly. My algorithm and the basic algorithm assuming the exact same access model, right? So it's a fair comparison, right? If you had some other way of measuring the observable that doesn't go through this basic algorithm, then I'm not claiming that we can speed that up. I'm just saying if your strategy was to do this basic algorithm, then we'll give you a quadratic speed up. Rhonda.
Sorry, I have to ask. The units don't work.
Oh, why is that?
Well, I mean, if the observable O is are you renormalizing or something?
Oh, sorry, in which one do the units not work?
So sigma in principle has units, right?
Oh, here.
So does epsilon.
No, but so does epsilon. Right? Epsilon is units of observable. Right?
Oh, I see. Okay.
So all of these, yeah, the epsilon comes here, but on the top there's somebody who cancels the units.
Good.
Right. Good. Yeah, units should always work. Yeah.
But for the above, don't you also need observable to be norm 1 or something?
For what?
For the above, the basic algorithm, don't you also need the observable to be norm 1?
No, you don't, right?
So if it wants to be block encoded, it has to be fit into a unitary.
Well, I'm not thinking of a blocking query. I'm just thinking you go to the basis of the observable. You just measure psi and O's eigenbasis. So that means you know O's eigenbasis. Go to that basis and just do a projective measurement. So yeah, this is very powerful. If for observables that can be large, like energy or something. Like it can genuinely be a large range, but maybe you know that your state is actually living in a low energy sector or whatever. So then you really do want to use some Chebyshev style argument. You don't want to suffer the max norm of the observable. I assume this is also how people do it in practice in the real world when they want to estimate observables at a potentially large norm. You just use Chebyshev. Yeah?
Yeah, you may already explain, but I just want to know what's the main difference between your algorithm and the general amplitude amplification. What's the main difference between your work and also Han?
Right, I didn't really explain, but maybe this example is good to explain what the main difference is. In our algorithm, you get sigma in the numerator, whereas in amplitude amplification, you'll get the max of the random variable, like the largest possible value that the random variable can take anywhere. And in general, that's worse, right? Like the sigma is always less than that. So that's the main advantage. So if you have a random variable that, for example, you know is bounded or something, and you know it's, like if you know that the standard deviation is very comparable to the largest value that the random variable can take, then you should not use our algorithm. You should just use amplitude estimation.
Yeah, I understand the results. I just
Right.
want to know
Your
algorithm, what's the difference?
Right. I haven't explained the algorithm at all. I'm still just telling you
Sure. Okay.
what we did, and now I'm telling you why you should care. But in the third part of the talk, I'll tell you what the algorithm is. So I'm still, in the applications part. Any questions about this application? Because, people might care about observables. And let me give you a third application. This is, I like this application. It's not like, I don't know if it's necessarily a useful application, but it's a very fun application. Maybe the computer scientists in the audience will like this application. So think of the following task. First, let's just think of a classical task. So I have a black box, and it either samples from a probability distribution Q or from a probability distribution R. You know what Q and R are, the distributions, like they're written down on a piece of paper explicitly. You know exactly what they are. But somebody hands you a box, and it just samples from one of them. And your task is to decide which box did you get. Did you get the Q box or did you get the R box? So what do you do? Like what is the, so my question is how many samples do you need to distinguish them with high probability, let's say 99% again? Certainly, it'll depend on how close Q and R are. Like, for example, if Q equals R, then of course you cannot tell them apart. And obviously, by continuity, if Q is extremely close to R, then you will take an extremely long time to tell them apart. So it has to depend on some distance measure of Q and R. In fact, it has to go 1 over this measure. So, okay, yeah, somebody want to guess what this distance measure is? KL divergence. Okay, any other guesses?
The swap test, right?
I'm thinking just classically, yeah. So these are two classical boxes, yeah. So you can't do a swap test or anything right now. Okay, so KL divergence is basically right, except it's like an asymmetric thing. So, I mean, I didn't tell you exactly what my metric was, but let's say you want to output the correct thing with the highest probability. So it's not an asymmetric metric where there's a null hypothesis is Q and you want to get R or whatever. But anyway, KL divergence is basically right. You need some symmetrized version of that. And the one that's most popular that, computer science types really like is this thing. It's called the Hellinger distance, presumably defined by somebody called Hellinger. And it's defined like this. And it turns out that this is the correct sample complexity. This is all classical. Okay, there's no quantum so far. So you can just compute this distance measure. It's just some kind of norm here. It's the square root of these vectors, L2 norm squared. And this is the sample complexity. So yeah, this is a fun fact to know. It's very useful. You just want to distinguish two distributions classically. And now we can ask the same question quantumly. So now we can come to the quantum world. So what's going on quantumly? Again, we're not given a black box for Q and R because then you cannot do anything with quantum algorithms. We need to be, again, in the same assumption we made before, that is you have the source code for this black box. In other words, you have some code written in your favorite programming language or a circuit or whatever that outputs or samples from this distribution. And this problem was considered a couple of years ago by Alexander Belovs, who showed that you can quantumly do this with the quadratic speedup. So this 1 over h squared becomes 1 over h. So that's pretty cool. So you get a full quadratic speedup for this task of distinguishing two probability distributions in the quantum world. And we can recover this result in our language in a very nice way, which is that I'll define an observable for you, or a random variable, whatever you want to call it, which is this object. And you evaluate this observable against the distribution that you were given, which is either Q or R. In one case, it'll evaluate to some value. In the other case, it'll evaluate a different value. And these two are well separated enough that you'll just know which of the two you came up with. And this algorithm that I described works both classically and quantumly. So this algorithm will, in fact, recover this bound and this bound to recover our bound, the quantum bound, you use our algorithm. To recover the classical bound, you use Chebyshev's inequality. So it's one nice unified algorithm for distinguishing two probability distributions that gives you the correct answer both quantumly and classically, just based on whether you plug in a classical optimal mean estimation algorithm or a quantum optimal mean estimation algorithm. Okay, so this is a fun fact, but I don't know any application of this like to something like observables or making money on the stock market. But anyway, I thought people might like this. Okay, there's a question back there.
Sure. Is there a particular reason you choose the Heilinger distance?
It's one thing you can put there that is optimal, like in the sense that it's a matching upper and lower bound. Like it is like up to constants, it is the thing to put there. There are a few other things you can put up there if you don't mind changing the constant, but this one I think is the cleanest definition.
What is the like access model you have? Like it seems like you're having to access some unitaries that involve both Q and R.
Oh, okay. So let's go back to just the classical settings. In the classical question, you knew what Q and R were explicitly. They were written down on a piece of paper, so you can compute arbitrary functions of Q and R. It's just somebody gives you a black box that's either sampling from Q or R. That's the only thing you don't know. So you can compute arbitrary functions of Q and R. You can run in exponential, or you can do whatever you feel like. You just know what Q and R are. It's the same setting in the quantum case. So I can write down this random variable. I can make measurements with respect to whatever. It's the only question is just this black box that was given to me. I need to tell whether it was Q or R. Any other questions? Yeah.
How should I relate xi to the sampling procedure? Because maybe I'm just a bit confused because here it would either sample from Q or from R, but how do I mix these together, so to say?
Ah, right. So this is the in quantum mechanics what we would call the observable, and the distribution is the thing that you don't know. So you compute the mean with respect to both the distributions. Just analytically, let's compute this. So let's call one mu sub q and one mu sub r. So mu sub q is sum over qi times xi, and mu sub r is sum over ri times xi. So it's the same xi. That's a number that I know. The q and r part is the part that I don't know, but that's the part that my black box is giving me. I compute this mean mu q or mu r. Of course, the black box is one of these two. Its average is going to be either mu q or mu r, but they're going to be well separated. So once you do this enough times, you'll just see it converging either towards mu q or mu r, and like when you see that, you just output, oh, it's mu q or it's r, because you just have to distinguish these two distributions. So that's how it fits into this setting of.
So I have to basically multiply this with respect to qi or ri.
That's right, and compute the to compute the expectation value, you would multiply this by qi or ri and sum over all i.
Okay.
Okay, good.
I'm just curious, what if we do not know Q and R, like two sample tests? So what's the?
But in what sense are you just like?
So you're just given two functions. I mean, like in classical world, you're given two random variables, and you want to tell whether the distribution is the same. So it's a two sample test.
Sorry, what do you mean? So like?
So you're given a pair of random variables, and you want to tell whether they are drawn from the same distribution.
You mean you're giving a pair of random variables or two probability distributions? And you want to tell them they're the same?
I guess the output, right?
The output of a distribution? Right.
Output,
okay.
And now your test is tell whether they're drawn from the same.
Oh, they're the same or different. Oh, I see. Right. I don't think that our results say anything about this. It is certainly a very well-studied problem classically. I don't know if it's quantumly studied. Yeah.
I have a related question, but you said that if the distributions are exactly the same, then you won't be able to tell them apart. So even if they're like very similar to each other, what quantities would we know to know how many samples we need to draw?
This h distance measure. So as they get closer and closer, this tends to 0, right? In fact, when
for h, we need to know the distribution itself, right?
Which we do. So we know the distributions. We just don't. We're given a black box that's one of the two distributions. We just don't know which black box we're given. Yeah. Yeah.
How does this compare with a different metric, like the swap test? Because that gives you the overlap of the two distribution, and that's exponentially efficient.
So if you had like pure quantum state versions of these distributions, so if you had like square root qi ket I summed over all I, then the swap test would be a better thing to do. But we're not assuming that we have that, because in the classical case, of course, we just have a classical distribution. In the quantum case, we assume that we have garbage. So we have sum over I square root qi ket I, and then there's some garbage entangled state. So you cannot do the swap test because the entangled state.
You can always convert that into amplitude, and then you compare that. You do the swap test. So you mean all your information is in a computational basis, is that right?
No,
Or
that's not the problem.
amplitude?
I'm saying.
If you have a quantum state.
I'm saying it's like if you have this guy, then you can do the swap test. That's fine. But if you have this guy, and here you have some garbage.
Yeah, you can still do that.
Then the swap test doesn't work. And in fact, in general, you cannot convert this to this unless you make exponentially many copies of this. So
I think if you know how that garbage state is generated, you can.
that's right. But this is not known to you, right? I mean, like this could be some arbitrarily complicated thing that's a function of the source code. Like the source code might be doing some crazy stuff inside it, right? It might be doing some arithmetic. It might be doing something completely outside your control. And this garbage can be extremely long. Right?
Can you write the R state? So how do you represent?
Yeah. So the R state will be like this, but it'll have
garbage is the same.
No, it'll be different. Yeah, you have no control over the garbage whatsoever. So yes, you want to do this versus the R state, but this is something else. Let me call it G garbage. This state has no relationship with that state because you don't know anything about the source code of the two circuits, right? That produce Q and R. Like the thing that's producing Q and R have completely different logics internally, and therefore produce different garbage. Yep. Question there.
What is the reason for the specific form of the random variables?
How do we choose this random variable?
Yes. Is there any intuition behind it, or?
That's a very good question. I don't think I can offer anything. We tried a few things, and if you take this random variable and compute its expectation value versus Q and R, the expectation value is exactly the Hellinger distance. It's plus the Hellinger distance in one case and minus the Hellinger distance in the other case. So it works out to be just the thing you need it to be. Yeah, we tried a bunch of things and we tried to make the equations work, and then finally we settled on this thing that looks really pretty, but I'm sure there's a nice way to derive it, but we don't have one. Question, yeah.
When you compute the mean of the random variable, if it's less than 0 or greater than 0, is that how you distinguish, or what is the?
Yeah, for example. Here, because they're exactly symmetric around 0, so that, yeah. Okay, since I'm short on time, maybe I should tell you a little bit about how our algorithm works. I have till the hour, I guess, with questions, since we had questions during, right? Okay, good. I can tell you how the algorithm works. The algorithm is not complicated. The analysis is complicated, but I'm not going to walk you through some proof because that would be crazy. I'll just tell you what the algorithm is. And okay, so the top is the main result, as I said before. Order n samples, output an estimate mu, such that the additive guarantee is sigma over n. Okay, cool. That's the problem we want to solve. And what we do is we reduce it to another problem using a very popular thing in computer science, a reduction, which is just a bunch of things, involves things like binary search, exponential search, majority voting, whatever. And it includes a quantum algorithm as well, which I won't talk about any of these things because none of them are due to us. These are just like, you could say, known things. They're not all trivial things. And for example, this is a very interesting algorithm, but let me skip all this because that's not our contribution. But we just reduce this more general problem to an easier problem. And let me convince you that this easier problem is a special case of the general problem. So, and from now on, we'll just focus on the easy problem because, take my word for it, you can reduce one way to the other. But let me convince you that the easier problem is indeed a special case. So in the easier problem, we have a different guarantee. You are promised something now about the random variable, unlike our original question where we had no promise on the random variable. Now you're promised that the second moment is bounded by 1. And this promise is even stronger than knowing that sigma is less than 1, because the second moment is like, the sigma is like second moment minus the mean squared or something. So knowing that this is less than 1 means sigma is definitely less than 1. And furthermore, you're promised a second thing, that the mean is either kind of small, it's less than epsilon over 2 in absolute value, or it's kind of big. It's between epsilon and 2 epsilon in absolute value. So I'm giving you a lot of extra information in this simpler task. That's why it's simpler. And the budget that you have is 1 over epsilon. So I'm allowing you 1 over epsilon samples. And the reason why this is a special case of this is because, so what's going on here? As I said, we've already assumed this is less than 1, so sigma is less than 1. And I only need to distinguish these two cases. And to distinguish these two cases, all I need is to estimate the mean to additive error, let's say epsilon divided by 4 or something like that. And I have a budget of 1 over epsilon. And so how would I do it here? I would choose n to be like order 1 over epsilon, right? So like more precisely, I would choose it to be like, I don't know, 4 over epsilon or something that'll give me, whatever. The thing that gives me an additive error of epsilon over 4, and that is exactly order 1 over epsilon. So this problem is indeed a special case of that problem. And for the rest of the slides, I just want to focus on this problem. Does that make sense to everyone?
The O1 over epsilon, what does the constant depend on?
What does the constant depend on? I guess it's just some fixed constant that we didn't bother to write down. Like in theory, I guess one could compute it. A universal constant, exactly. Yeah. Like 10 or something. Yeah. Good. Okay. So right. So our algorithm is going to solve this simple problem. And what is our algorithm going to look like? In fact, it's going to look like very similar to Grover's algorithm. So this is great because everybody likes Grover's algorithm. Grover's algorithm is simple. And the one twist on Grover's algorithm is our algorithm is Grover's algorithm, but with complex phases. So Grover's algorithm, if you recall, basically has only real numbers. And we're going to use complex numbers. That's like the main diff with respect to Grover's algorithm. So let me give you a quick recap of Grover's algorithm. Maybe everybody knows, but why not? So Grover's algorithm has this format. You alternate between two unitaries. The first unitary, I'm going to call it R for reflection. It's a reflection about the uniform superposition. So you do this identity minus 2 UU, where U is the uniform superposition. That's cool. We're also actually going to use the exact same unitary, R. So that's great. And notice that in Grover's algorithm and in our algorithm, this unitary has nothing to do with the input to the problem. It's always a fixed unitary. It's always this reflection. Cool. So in Grover's algorithm, of course, the input has to enter somewhere. It enters to the second unitary. And the second unitary in Grover's algorithm is, I'm going to call it the phase oracle. I'm going to call it P for phase. And it performs the following map. It takes ket I and maps it to ket I if xi is 0, and it maps it to -1 times ket I if xi is 1. So that's the phase oracle. And this is the part that we'll have to change, because in Grover's problem, there's only two possible values that xi can take. Xi can be 0 or xi can be 1. For us, xi is a real number with basically no bound at all. It's between -infinity and +infinity. So this map is not a good choice for us. So we have to change the second part. And so how do we change that? We want some way to map a real number between -infinity and +infinity to a phase, because that's all the freedom we have over here. Like, we just have a phase. And you had a guess for that? That might work. Yeah, we choose a different map, but this is the map we choose. Like, if you want to go from -infinity to +infinity to a phase, which is, in other words, you want to go from -infinity to +infinity to like -pi to pi, you can just take arctan and multiply it by 2 or whatever. That works. And if you want some intuition for what that looks like, here are some graphs. If you think about it like, if you want to think about it like this is what the, I guess we take -2 arctan for some reason. Yeah, so what does the arctan function look like? Basically, as you go further and further closer to infinity, it gets closer to -pi. Here it goes close to +pi, and close to the origin, it's close to 0. Okay, maybe you already know what arctan looks like, but that's one picture. There's another way of thinking of arctan, which is also kind of cute. It tells you the arctan of y, you draw these two lines, 1 + iy and 1 - iy in the complex plane. And arctan of y is like the angle between these two lines. Or 2 arctan is the angle between those. Whatever. Anyway, it's some real number, it's some function that you can compute. So cool, that's the algorithm. Okay, yeah, so well, I didn't completely specify the algorithm, but I've told you the two unitaries that are part of the algorithm. The first unitary is the same unitary as in Grover's algorithm. It's a reflection about the uniform superposition. That's great. We know how to implement that. That's easy to implement. The second unitary is this phase oracle over here. But this is a diagonal operator, so it's also easy to implement. How do you implement this on a quantum algorithm? You just query the oracle. It tells you what xi is. Or sorry, you know these xi's. You just compute it, put it into the phase. Right, so yeah. If hopefully everybody remembers the setting that you had some oracle, you could tell it I, and it would tell you what xi was. So you ask it, hey, what's xi? It tells you what xi is. You compute alpha of xi, you put it in the phase, and you uncompute it. Maybe it takes two queries or whatever. But with two queries to the oracle, you can implement this operator. It's diagonal, so like it's clear, it's easy. The other operator, which is the non-diagonal operator, is in fact the same one you use in Grover's algorithm. So that's easy too. So two easy operators, and the algorithm is going to be built out of just these two guys. Okay, any questions about the definitions of these two operators? Yeah.
So arctan, if it's shaped like this, means you're much more sensitive to some regions of xi than other regions of xi.
That isn't right. That is right.
Does that matter at all?
Yeah, because we already have a bound on the second moment of the random variable. So most likely the random variable is hanging out pretty close to 0, right? Because it can't take values like a billion, because if it did, it would take that with probability like 1 over a billion squared or something. And then maybe that point doesn't really matter, because you just want an epsilon approximation anyway. So you don't actually care about values of the random variable that are super duper large.
Is there some bit that you can use if you know something about your random variable where you can scale the range of your arctan variation that you can make use of to make things better?
That's essentially what our condition enforcing the second moment less than 1 is secretly doing. Yeah. So if you knew something else, then I would say just bring it to the standard form of the second moment being less than 1. That would, yeah. Good. These two operators make sense to everyone. R and P, they're both simple, they're easy to implement. And now my algorithm will only use these two guys. And in fact, the algorithm's main technical claim, like the only theorem that really has to be proved, is this following sentence here. The claim is that the state ket u, which was the uniform superposition that I had a couple of slides ago, it's just literally the uniform superposition over all basis states. It has very high overlap with an eigenvector of this unitary, which is the product of the two unitaries I just said. So that's a unitary you can implement on your quantum computer. And its eigenvalue encodes the mean. So just take my word for it that this technical claim is true. And in fact, for the moment, let's say instead of saying it has high overlap, let's say it literally is an eigenvector. So that'll give us some intuition for what's going to happen. You have a state. It is literally an eigenvector of a unitary that you know how to implement on a quantum computer. The state is very easy to prepare on a quantum computer. And the eigenvalue is hiding some information. You just want to know if the eigenvalue is, what was the promise? It's either epsilon over 2 or epsilon. So you want to know the eigenvalue is either e to the I epsilon or it's e to the I 2 epsilon, whatever. So what well-known popular quantum algorithm will you use to solve this task?
Phase estimation.
Phase estimation, okay.
So what is U again?
U is just the product of these two easy unitaries that I described before.
No. What did that?
Ket U is the uniform superposition.
Oh, I see.
Yeah, it's just literally sum over I, ket I, appropriately normalized. So yeah, phase estimation is the algorithm.
How do you know? How do you set up that U state?
The ket U state?
Ket U is high overlap. Yeah.
Ket U is just this. Yeah, let me just write it here. It is just literally this 1 over. So it's the uniform superposition. You just create the uniform superposition in a quantum computer the way you usually do. You just start out with a bunch of qubits, Hadamard in 0, Hadamard.
Yeah, but how do you know that has high overlap?
Yeah. This is the main technical claim this is why we wrote a paper. Yeah, this is the hard part. This takes several pages to prove, and this is the part that, this is the part I'm not going to explain because it's very technical. But what I want to impress upon you is that the algorithm is very straightforward. As somebody, or maybe many people in the audience already guessed, you can just literally run phase estimation with precision epsilon. And if you remember the complexity of phase estimation, the complexity of phase estimation is inversely proportional to the precision. So if you want to do it at epsilon or 4, you'll need 1 over epsilon uses of phase estimation. That's where the 1 over epsilon comes from. That's the end of the algorithm. Or you can do something a little more trivial. This is like just a fun fact about phase estimation that if you literally trying to decide between two different eigenvalues, you don't actually need to do phase estimation. Like all you can do is you power up the unitary so that these two eigenvalues keep moving until one of them is like 1 and the other one is -1. And then you can tell them apart with the Hadamard test. It's a fun fact about phase estimation. So phase estimation does much more than this, but if I promise to you that you have to tell only two different eigenvalues apart, you actually don't need to run the whole machinery of phase estimation. You can just get by with like 1 additional qubit. But anyway, that's just a implementation detail if you care about saving qubits. But that's the algorithm. And yeah, since I'm out of time, maybe I'll just stop here and take questions. I feel like there's going to be more questions. Yeah.